Welcome to another lecture in construction equipment, and today we're going to talk about hydraulic excavators. We're going to start talking about different types of equipment, their production rates, their cycle times, etc. We're going to have a few ideas about what are these equipment used for and how to maximize the efficiency of their use. So the first piece of equipment that we're going to start talking about is a set of types of equipment called hydraulic excavators, used primarily for excavation. So what are they? An excavator is a power-driven digging machine. So the primary use is to dig or to excavate. Major types include hydraulic excavators, shovels, draglines, hoes or backhoes, and clamshells. All of these are considered under one major group of equipment called hydraulic excavators. Other equipment such as dozers, loaders, and scrapers may also be used as excavators, although that's not the primary use of these equipment. So if we do not have any of the first type or first group, backhoes, shovels, clamshells, draglines, and so on, to a certain extent we can use the bulldozers or the loaders or the scrapers in a suboptimal use just to excavate, although that's not their primary use, as I just mentioned. So here are some samples. Here we have a dragline. This is a backhoe, and this is a clamshell. As you can see, all of them are used for excavation for different types of soils, for different types of projects. Now we need to start talking about the production of the excavator. How can we measure its production? The production of an excavator can be simply calculated from the equation. Production per hour is equal to volume per cycle times cycles per hour. So depending on the volume that you can achieve per cycle, whether it's on the bucket or the dragline or the clamshell, its capacity, times how many cycles per hour, how many repetitive cycles can we achieve per hour. The volume per cycle depends on the rated bucket capacity and the bucket fill factor. So there are two major elements here: rated bucket capacity, which is the size of the bucket, and the bucket fill factor, how far can you fill it. And here we have a couple of tables that show for different types of machines what would be the rated bucket capacity, and for different types of materials what would be the bucket fill factor. So for example, for a backhoe or shovel that's cable, the rated bucket capacity is the struck volume. So if the bucket size is, let's say, 2 cubic yards, the struck volume means that there's no heap, just at the surface of the bucket. That's the maximum capacity. And if it's a hydraulic backhoe or shovel, then the heaped volume at a 1-to-1 angle of repose. So there's going to be a heap on top of the rated capacity of the bucket, plus that heap, which is going to be something like a cone or a pyramid, at that angle of slope of 1-to-1, which is the angle where the soil can support itself without any additional support. For clamshells, it's going to be the plate line or water line volume. For the drag line, 90% of the struck volume, and we're going to see why. Because once you drag that bucket and you start lifting it, some soil is going to fall down, so that amount for about 10% of the volume of the bucket. And for a loader, which is a front loader, not a backhoe, a front loader lifts from the front, is going to be a heaped volume at 2-to-1 angle of repose. So with the hydraulic backhoe is going to be 1-to-1 angle of repose. With the loader, it's going to be 2-to-1 angle of repose. Now, based on the material itself that we're going to carry inside that bucket, the finer the grain of that material, the more volume we can carry. Of course, the coarser the grain, the less volume. So we can see here, for example, for common earth or loam with very fine particles, the bucket fill factor is going to be anywhere between 0.8 to 1.1, the capacity or the size of that bucket. For sand or gravel, it's going to be anywhere between 0.9 and 1. For hard clay, 0.65 to 0.95. For wet clay, 0.5 to 0.9. For rock that's well blasted, 0.7 to 0.9. For rock that's poorly blasted, it's going to be much less than that, 0.4 to 0.7, because of the angular shape of these rock parts or parts of rock, and the amount of air that's going to be in between, because they're not going to be interlocking together in an efficient way. So let's look at an example here. Estimate the hourly production of a loader with a bucket heaped capacity of 5 cubic yards. The soil is sand, and the load factor, which is to convert from loose to bank volume, that's going to take care of the swell, is 0.8. The cycle time for the loader is 1 minute and 30 seconds, which is basically 90 seconds. And the job efficiency is 80%, which means out of every hour we can use 80%, which is 48 minutes. So to solve this problem, we need to get the number of cycles per hour times the bucket capacity. The bucket load is going to be equal to the fill factor times the bucket heaped capacity, which is 0.9 times 4.5. Here we have, we're going to look at the table. That's going to give us that 0.9. And the bucket heaped capacity was 5 cubic yards, and that's going to be in loose cubic yards. Then to convert from loose cubic yards to bank cubic yards, we multiply by the load factor. So 4.5 loose cubic yards times 0.8 gives us 3.6 bank cubic yards. So the capacity per cycle is 3.6 bank cubic yards. The next part is how many cycles can we have per hour? Number of cycles per hour is 60 minutes divided by the cycle time in minutes. But we were given the cycle times in minutes, in seconds, which is 90 seconds, or in minutes, which is 1.5 minutes. So 60 divided by 1.5 gives 40 cycles per hour. However, that's assuming that we're working 60 minutes per hour. We know that we're not going to be working 60 minutes per hour, but only 48. So we have to multiply by the efficiency, which is 0.8. And that gives us a total of 115.2 bank cubic yards per hour. Now remember that this 0.9 came from a table like this. We were looking at sand and gravel. It's anywhere between 0.9 and 1.0. And here we are told that what type of soil do we have? The soil is sand. So that's why we use the 0.9. Okay, so here's the table that we used, which is the 0.9 to get that 0.9 here at the top. So the total production per hour is going to be 115 bank cubic yards per hour. If the question was to calculate that hourly production in loose cubic yards, we wouldn't have to multiply by the load factor in this case. So it's going to be 4.5 loose cubic yards instead of 3.6 times 40 cycles times 0.8, and that would give a different number that's going to be in loose cubic yards per hour. So always make sure what the question is asking about. Is it asking about bank cubic yards or loose cubic yards? For the hydraulic excavators also, we have something called a hydraulic hoe or hydraulic excavator backhoe, depending on whether the bucket is lifting forward or is it lifting backward. It digs by pulling the dipper back towards the machine if it's a backhoe. When the dipper is filled, it's curled up to reduce the spillage so that it can maintain the maximum volume of soil inside that bucket. And here's the example. This is the dipper or the bucket. So you extend the arm, you dig, and then you drag the arm backwards and lift the bucket to maintain the soil in the bucket. This, of course, is hydraulically driven, so all of these are hydraulic pumps or cylinders. What is it used for? It's used for trenching work. If you want to dig a trench, and the best production is going to be if the trench has the same width as the width of the bucket itself. It can also lay pipes, pull trench shields or sheet piles, and backfill the trench by placing the soil back after laying the pipes. The dipping width of the bucket should match the trench width to maximize the production. We can also have telescoping booms, which are going to replace the articulated booms. In the previous picture we had an articulated boom, but you can also have telescoping booms that can extend hydraulically as well. The production rate for that excavator is going to be, the generic equation is going to be production in loose cubic yards per hour. Notice now that this is in loose cubic yards per hour, is equal to C times S times V times B times E. Let's learn about each one of these symbols. C is the number of cycles per hour. Basically the production is going to be volume per cycle times number of cycles per hour. This is in a nutshell, how we calculate the production. But what are the details now? The C is the number of cycles per hour. S is the swing depth factor. We're going to see that in a table in just a second. V is the heaped bucket volume. B is the bucket fill factor, which would vary from one type of soil to another. And E is the job efficiency. How many minutes can we work per hour? If that efficiency is 80%, then it's 48 minutes. If it's 75%, that is 45 minutes, and so on. How do we get the number of minutes? By multiplying that factor times 60. So 80% is 80 times 60, which gives 48 minutes. 75%, 75.75 times 60, which gives the 45 minutes. So the effect of job conditions. Now this is something that you as a project manager can control on site to improve the production rate of that equipment. So we have different job conditions varying from excellent to severe, which is extremely poor. Depending on the backhoe bucket size, we can estimate the cycle time. So under excellent conditions, let's say we have a 2 cubic yard bucket. The 2 cubic yard is going to be somewhere between these two. So under excellent conditions, the cycle time is going to be anywhere between 15 to 16 seconds. So 15 and a half would be fine, 15 would be fine, 16 would be fine. Above average, which is not excellent, a little bit longer. It's going to take 17 instead of 15 seconds. Severe, that's the worst type of conditions, is going to take 25 seconds instead of 15. Now imagine if every cycle is extended by 10 seconds, that means that you're going to have a total reduced number of cycles per hour, which is going to reduce the total production rate. Here is an example of what do we mean by excellent and so on. So excellent conditions are characterized as easy digging, unpacked earth, including sand, ditch cleaning, etc. Some loose soil. Digging to less than 40% of the machine's maximum digging depth. So again, you're not going to extend the boom to the maximum. Swing angles less than 30%. When you swing the piece of equipment to dump the soil into a truck or somewhere else. Dump into a spoil pile, so not into a truck, for example, because if you're dumping into a truck, you have to adjust to make sure that you're dumping exactly in a proper location. But if you're dumping into a spoil pile, you have more latitude. No obstructions, so there's no fence, and you can see clearly the area where you're going to be dumping the soil. That would be excellent conditions. With any change of these conditions, it's going to reduce the efficiency and increase the cycle time. Above average conditions are characterized as medium digging. Here it was easy, now it's medium. Packed earth, dry clay, soil with less than 25% rock content. The depth also, instead of being only 40% of the maximum digging depth, now it's up to 50% of the maximum digging depth. The angle, the swing angle here was only 30%. Here it has increased to 60%. Large dump target and a few obstructions. So that's going to increase the cycle time and reduce production rate. And so on. You can see with the average, we're going to have hard-packed soil. Depth 70% instead of 50. Swing angle 90 degrees instead of 30 or 60, and so on. Under severe conditions, characterized as tough digging, sandstone, shale, limestone, hard frost. Depth over 90% of the machine maximum digging depth, so you're reaching almost to the maximum. and the swing angle over 120 degrees, so almost turning backwards to download that bucket into a dump target. And it's a small dump target, so a small dump truck, for example, which requires more adjustment and more maneuvering. So basically that's how we estimate the efficiency of the job. In a problem that I might give you on a test or something, I'm going to give you what would be the type of job, so you don't have to worry about all of these. Or I'm going to give you some of these and I'm going to give you the table, and you have to estimate based on this table which one would it be. Would it be above average, excellent, average, severe, etc. This information, by the way, was extracted from a Caterpillar performance handbook for a Caterpillar backhoe. Another type of equipment that's used also for excavation is shovels, also called front shovel or hydraulic excavator front shovel. Digs with a combination of crowding, which is a down force, and breakout, which is a forward force. So this is the opposite of the backhoe. The backhoe brings the soil backwards. Now this is going to lift it forward. Has limited ability to dig below the track level. So if the best option or the best production is going to be if you're digging at the track level. Below that is going to have the risk of over tipping or falling forward, so that would be a balance issue. And here's the example. As you can see, the bucket is facing forward. Same arm, same adjustments as we had for the backhoe. The main difference is in the location of the hydraulic cylinder and the orientation of the bucket. When you apply this, you're going to hit the ground with the crowding force, which is digging down, and then with the breakout force moving it up to load that soil in your truck or whatever. The shovel production, exactly like the backhoe, it's going to be calculating using the same equation, which is CSVBE, with, again, we know what each one of these stands for. The production is mainly affected by the swing angle and the lost time during the production cycle. The angle of swing between digging and dumping should be kept to a minimum to improve production. So if you're going to dump that soil into a truck, try to locate or to position that truck very close to the point of excavation so that you don't have to rotate more than 30 to 45 degrees. To calculate the shovel production, other factors to improve the production include having a level floor or cut. Again, this is something that you as a project manager can adjust to prepare for the excavation so that the shovel is on a level playground or a level ground. Moving frequently to be closer to the working face. Keeping the digger teeth sharp. This is something, again, that you can inspect. And better training for the operator. The more trained and skilled the operator would be, the higher the production rate that you're going to get. So the ideal production is going to be equal to the bucket capacity times the fill factor, which is a property of the soil that you're digging, divided by the ideal cycle time. And the ideal cycle time, as we mentioned, is going to be obtained from table. So here, for example, are different types of materials. Moist loam or sandy clay, the fill factor is going to be between 1 and 1.1 of the rated capacity of the bucket. For sand and gravel, it's going to be anywhere between 0.95 to 1.1. For poorly blasted rock, it's going to be anywhere between 0.4 and 0.5. And again, that's obtained from the Caterpillar Performance Handbook for that type of shovel. The ideal shovel productivity in bank cubic yards per hour. Now, this is measured in bank cubic yards, depending on the bucket capacity, the bucket rated capacity. It shows here for, let's say, a 2 cubic yard bucket. Moist loam is going to be 355 bank cubic yards. For tough clay, it's going to be 265 bank cubic yards. For poorly blasted rock, it's going to be only 160 bank cubic yards. The angle of swing, as we mentioned, is going to affect the cycle time with a factor. So if the angle of swing, if the optimum depth is 40% of the maximum, and the swing angle is 90 degrees, then that's going to have a factor of 0.8. It's going to reduce your production rate by a factor of 0.8. If the angle is 45 degrees, the reduction is going to be only 7%. This is a reduction of 20%. This is only 7%. If the maximum depth, if the optimum depth is 160%, as you can see, we're going to have here different production rates. On the job conditions, which is again something that you can control, like for example cleaning the site, having no obstacles, having a clear line of sight or line of view for the operator, having the equipment close to the to your excavator or your shovel, so that to minimize any travel time. So if it's excellent, you get 0.84%. If it's poor, you get 0.72%, and so on. So these are the job conditions, and these are the management conditions. The management conditions, again, these are something that you can control as a project manager. Let's look at an example again to make things much clearer. A contractor has a project to excavate an apartment complex and must construct a 3-foot compacted fill to support a parking garage. The borrow site, where you're going to get your soil, is 3 miles from the construction site. A 10 cubic yard dump truck will be used, and 10 cubic yard dump trucks will be used to haul the needed fill. A 2 cubic yard shovel will be used to load the dump trucks. So how many cycles is it going to take for the shovel to fill the truck? This is 2 cubic yards, this is 10 cubic yards, so we're talking about 5 cycles to fill one truck. The material is tough, dry clay with a swell of 35%. The height of the cut at the borrow site is 11.6 feet, and the angle of swing of the shovel is 150 degrees. That's quite large. Estimate the ideal production using the table, and estimate the actual production for good job and management conditions. The optimum digging depth of the shovel is 9.8 feet. Optimum digging depth is 9.8 feet, and the actual depth of cut is going to be 11.6 feet. So the ideal production from the table is 265 bank cubic yards per hour. Let's look at that table. So we have 2 cubic yards bucket, and we have tough clay. Therefore the ideal production rate is going to be 265 bank cubic yards per hour. The fill factor is for that tough clay, as we have seen before in the table, is 1.05. That's an average. The cycle time for the average job conditions for 2 cubic yards, which is going to be somewhere between 1 to 2 and 2 to 3. We're going to take the average of the two. So between 20 seconds and 22 seconds, we selected 21 seconds, which is average. Therefore, the production is going to be equal to the bucket capacity times the fill factor divided by the ideal cycle time. The bucket capacity, 2 cubic yards. The fill factor, 1.05, depending on the type of soil. And divided by the cycle time, which is 21 seconds that we obtained from here. And we basically 21 divided by 3600 to convert from seconds to hours. So we put the 3600 above here. Divided also by the load factor to convert from loose to bank cubic yards based on the swell factor that we already had, which is 35%. The percent of optimum depth for this excavating operation is, now we have the optimum is 9.8, the actual is 11.8, so that's equivalent to 120% of the optimum. Using the percent optimum depth, 120, and the angle of swing 150 degrees. And the tables that we have seen on the previous slides, we get here, we find from the table that 120% with 150 degrees gives 0.77. For good operating and job management conditions, the factor is good, and good is going to be 0.75. Therefore, the actual productivity is going to be the optimum, which is 265 bank cubic yards per hour, times 0.77 times 0.75, and that gives 153 bank cubic yards per hour. Another type of equipment is the draglines. So a dragline is a very versatile machine with longest reach for digging and dumping. It has a longer arm and is best used for soft to medium hard materials, sand, clay, etc. The bucket teeth and weight produce digging action as the dragline pulls the bucket back across the ground surface. So basically we rely on the weight of that bucket falling under gravity and then pulling that bucket to fill it with soil. The higher the point of attachment, the better penetration, because of higher altitude is going to fall with a bigger impact on the soil. And here's an example. This is basically the bucket of that drag line. And here it shows long arm. You reach, you drop it, and then you drag it to fill it with soil. And that's another view. So of course, the longer the boom, the higher the point of dropping that bucket, the more efficient you're going to be in filling that bucket. You drag that cable to bring it back, and then you're going to turn and dump it in a truck or a pile of soil. The expected production is equal to ideal output from the tables times swing depth factor times efficiency, because again, based on the depth and based on the swing of the drag line, that's going to affect your cycle time. Most efficient digging area is located within 15-degree angles forward and back of a vertical line through the boom point. So if you drop the bucket vertically, 15 degrees front and 15 degrees back, that's going to be the most efficient digging for that drag line. Deep cuts should be excavated in layers with a thickness as close to the optimum depth of cut as possible. So you can do it in different layers. Once you finish one, you move to the following layer. Now again, here are some sample production rates and so on. If we're talking about a drag line with a bucket capacity of 2 cubic yards, digging through moist loam or light sandy clay is going to have an optimum depth of cut of 8 feet. If you're digging through wet, sticky clay, the optimum depth of cut for the 2 cubic yards is going to be 11.8 feet. The correction factor based on the angle of swing, again, the more the angle of swing, the lower the production rate. So again, based on the percent of optimum depth, let's say we're talking about 100% of the optimum depth and an angle of swing of 90 degrees, that's going to give you an efficiency of 1, which is 100%. If it's 30 degrees, it's going to give you an efficiency of 1.3 to 132%. If it's 180 degrees, it's going to give you an efficiency of 77%. And the ideal dragline productivity in bank cubic yards per hour, again, based on the type of soil and the size of the bucket, similar to what we have seen before, is going to give you what would be the ideal production rate based on the bucket size. Another piece of equipment also used for excavation is the clamshell. It has a substitute attachment for the drag line. So instead of the bucket of the drag line, you're going to have the clamshell capable of digging at higher depth, so you can descend it into a well, for example, or a shaft, and it can grab the soil and lift it vertically. It lacks positive digging action and lateral control of the shovel or backhoe. So the backhoe and the shovel are much better for lateral control and positive digging action, which means hitting with a certain force. This relies primarily on the weight of the clamshell itself. Used for excavating vertical shafts and footings. So again, same machine as we had with the drag line. The only difference here is that we're going to drop this vertically, which is the clamshell, and it's going to grab the soil. You're going to lift it, turn, and dump it wherever you need to. And that's again is a magnified view of the clamshell itself. Here it shows that it can dig, especially in marine conditions and in wet conditions. A clamshell would be a very good machine to use. Production is based on the equation, again same generic equation, volume per cycle times cycles per hour. The maximum load should be limited to 80% of safe lifting capacity for rubber tired equipment and 90% for crawler mounted equipment, just because of issues of stability of the equipment itself. We don't want it to again tip over. Other factors to improve the production rate for the clamshell include having the dumping radius same as the digging radius. So again, you're not going to move the clamshell along the boom. You're going to lift the soil, turn, and dump the soil in a truck or a soil pile. Keeping the machine level to avoid swinging uphill or downhill, which is going to affect issues of stability and issues of production rate as well. So based on the angle of swing, as you can see, if it's a 90 degree, that's going to give you the optimum swing. If it's less than that, it's going to increase the production rate because of a shorter swing cycle. And again, similar to what we have seen before, depending on the ideal production rate is going to depend on the bucket size and the type of soil that you are digging. So let's look at an example one more time. A contractor has decided to use a 2 cubic yard clamshell mounted on a crawler crane to excavate for the foundations of 3 concrete piers for a highway bridge. The excavated material will be dumped in stockpiles for later use in backfilling. The material is common earth, and the average angle of swing is 120 degrees. Job and management conditions are good. What's the estimated productivity of the clamshell in bank cubic yards per hour? So, the estimated ideal productivity for a 2 cubic yard for common earth is 160 bank cubic yards per hour. The angle of swing is 120 degrees, so the correction factor for the angle of swing is 0.91, and the good job and management conditions from the previous tables is 0.75. Therefore, the production rate is going to be 160 bank cubic yards per hour times 0.91 times 0.75, and that gives 109 bank cubic yards per hour. So, in this lecture we have learned about what are the different types of excavation equipment, earth moving equipment for excavation primarily. We talked about the shovel, the backhoe, the drag line, and the clamshell. We looked at the different factors affecting their production rate and how many of these factors can be controlled by the project manager by improving the site layout and improving the location of the equipment and the dumping equipment and so on and so forth. So all of this is within your control, and I'll be glad to answer any questions related to that in class. Well, thank you, and see you next time in another lecture.